Archimedes' principle says that any object in a fluid experiences an upward buoyant force that's equal to the weight of the fluid that the object displaces. So, an object that is immersed in a fluid, you can see here if initially we had filled this up right to the line there, as soon as we put this rock in, that rock is going to displace some of the water, and the water level will rise. And if we get it just right, that extra water is going to run down here, boop, into that beaker, and we're going to catch it. And numerically, the volume of that liquid is the same as the volume of this submerged object. Here's another case here you could do in the lab. The water level initially is at 20 milliliters, let's say. When we put an object in with a very small string, the level goes up to, let's say, 23. So the volume of this object would be 23 minus 20 milliliters, about 3 milliliters. For a floating object, the displaced fluid's weight is equal to the object's weight. For a floating object, the displaced fluid's volume is less than the object's volume. Let's say we have here a floating object. There's the surface of the liquid. That right there is the amount of fluid that has been displaced. Not the entire volume of the object, just this volume right here. That much fluid weighs the same as the object. The buoyant force is equal to the weight of the fluid displaced. This displaced fluid has a certain weight. That weight equals the buoyant force. And since this object is floating, the buoyant force and the weight of the object must numerically be equal. When this tanker is loaded with oil, the red water line will be submerged, leaving only the black part of the hull above water. So, as we put more oil on this tanker, the weight is going to increase. That's going to cause the tanker to sink, and because it sinks, it will displace more water, and the more water it displaces, the greater the buoyant force. Here's a pool ball floating in mercury. Pretty neat. Highly dense. 13,600 kilograms per cubic meter, unlike water, which is only about 1,000 kilograms per cubic meter. So mercury is incredibly dense, and you can float all kinds of neat things on it, like aluminum, iron, even lead can be made to float in mercury. Those floating objects have a buoyant force that is numerically equal to the weight of the fluid displaced. For floating objects, the object and the fluid densities are proportional to the displaced and the object volumes. So here's a handy equation that only works for floating objects. If you want to write that down, make sure you put a little note by it. It's only for floating objects. The density of the object times the volume of the object is equal to the density of the fluid times the volume of fluid that's displaced. This is what I call the floaty rho v equation, because we have rho v and rho v, floaty rho v. That helps me remember that. What about sunken objects? For sunken objects, the displaced fluid's weight must be less than the object's weight. That's why it's below the surface. That's why it's sunk. And the displaced fluid's volume is equal to the object's volume, because the entire object is submerged, so the displaced fluid's volume must be equal to the entire object's volume. So let's say we have here a sunken object. That much fluid has been displaced, the same as the object's volume. And that much fluid weighs less than the object does. That amount of fluid must weigh less. The weight of the object must be more than the weight of this displaced fluid. That's why the object is sunken. And if you wanted to, you could call the buoyant force the Archimedes force. So here's an equation for the buoyant force. It's the mass of the displaced fluid times the acceleration due to gravity. And from the density equation, if we rearrange that, we get this relation here, that the mass of the displaced fluid is equal to the density of the fluid times the volume displaced. And so if m displaced fluid is equal to rho v, then up here where I have mass of the displaced fluid, I can put rho v in there and multiply that by g, and I have an equivalent expression. So it is primarily the volume of the immersed object, not its weight or mass, that affects the buoyant force, particularly for submerged objects. So here's a picture of a life preserver, and this life preserver greatly increases your volume, but hardly increases your weight. And because it increases your volume, that greatly increases the buoyant force, enough so that you will float. So here are some final thoughts. Archimedes' principle says that the buoyant force, Fb, on an immersed object is equal to the weight of the fluid that is displaced. Several equations deal with the buoyant force. For floating objects only, here's what I call the floaty rho v equation. And for either floating or submerged objects, the buoyant force can be found from these relations.